In this section, we're going to start looking at taking derivatives and antiderivatives of vector-valued functions. So right here is our definition. So when I want to take the derivative with respect to t of our vector-valued function r, which will also denote the vector r prime of t, that's going to be equal to what I hope is a familiar looking limit, right? So r of t plus h minus r of t over h. So really this is the same exact scenario as our Calc 1 limit. In fact, let's go back to Calc 1 for a second. Maybe let's do this over here on the side. Make a little picture to go along with it, perhaps. Oops. See if I can do a vertical line here. All right, so we got this picture here, and let's go ahead and draw our function in there. And let's say that maybe right here is the value x that I would like to calculate the derivative at. So then over here on the side, that is f of x, right? It's the y value. All right, so what do? We go over a certain distance, x plus h, some value h, and we go up to that y value, and that y value is of course f of x plus h, and we take the slope of this line here that we call a secant line, right? And so the whole idea is that if you take that slope, right, which is f of x plus h minus f of x divided by x plus h minus x, and then you let h get really, really small. Of course, on the bottom, those x's go away, so you take the limit as h goes to 0. You let h get really, really small. The smaller that h gets, the closer together these points get, until they're so close together that it's basically just going to end up being the tangent line. So that's just a quick reminder of why it is that f prime of x is equal to this limit definition. It's the same thing here, and it's the same picture you can see down here. So what do? I take r of t. So here's the point going to the point P, r of t. Remember, r of t is a vector that goes from the origin to the point on the curve that is associated with t. But then I do r of t plus h. If I subtract those two vectors, I get this blue vector here. Okay? And so the closer and closer I make t and t plus h, then the vector becomes like this, then the vector becomes like this, until finally they're so close together that it becomes the pink one, which we call r prime of t. Okay? And so understand that what we've done here is we've found a vector, r prime of t, that is tangent to the point that we're interested in, tangent to the curve at the point that we're interested in. But it's the same definition. One of the things that you're also going to see us talk about is the unit tangent vector. And the unit tangent vector is just taking r prime and dividing it by its magnitude, so that we're guaranteed that it is a unit vector. So I will never use t, capital T, unless as a vector, unless I'm talking about a unit tangent vector. So if you ever see that symbol, you can assume it has unit length. All right, so now here's a theorem. Okay, so back in Calc 1, right? You get this definition and you work with it for like a day or two, and then your Calc 1 instructor has mercy on you and says, oh, by the way, there's actually a way easier way to do this. And then from then on, you kind of ignore the limit definition for a while. So we're going to kind of jump straight there. So, you can think, hey, Calc 3's the instructor's being nicer than in Calc 1. So we're just going to jump straight to the practicalities of it. If you want to find r prime of t, all you got to do is take the derivative of each individual function that gives x, y, and z. And the proof of this is, real straightforward. So the idea here is if I want r prime of t, right, we know that that's the limit as h goes to 0 of r of t plus h minus r of t divided by h. Okay, but r of t plus h minus r of t, as you see in the picture, right, this blue vector, it's a vector. So that means we can express that in terms of a vector. So what I'll do here is I'll just write, this is the limit as h goes to 0 of, we'll have f of t plus h minus f of t, g of t plus h minus g of t, and then h of t plus, oh, this is bad form here. Sorry, I'm using h twice. That's bad form on my part. Sorry, but I think you get the idea. It's not so complicated of a proof that I think I'm going to abandon it now. And then we're still dividing by h overall, so that means I can just think of it as dividing by h in each component. But of course, those are just individually the limit definition of a derivative for f, g, and h. So at the end of the day, all we got to do, find the function, and as long as it's differentiable, find the function that represents x, y, and z, take their derivatives, and there you go. There's r prime. All right, so let's do an example here. First of all, it just says find the derivative of r of t if r is this vector valued function here. Okay, so we can do that. So r prime of t, we can just go through here. The derivative of this, we're going to use the power rule, 10t minus 1 as my x component. But then the derivative of 2t is just 2, and the derivative of 4t is just 4. So there's my derivative function for this vector valued function here. Now find the unit tangent vector. Okay, so that means, right, that I'm going to take r prime of t, divided by the magnitude of r prime of t. So that's going to be 10t minus 1, 2, 4, divided by, the magnitude will be the square root of the x component squared, y component plus the y component squared plus the z component squared. And I can do a little bit of simplifying here, I think. So in the denominator, we've got 100t squared minus 20t plus 1 plus 4 plus 16. All right, so that means we have this as our final answer. So what's the point of this? The point of this is that then you can plug in any value of t, and instead of just having r prime, now you have a unit tangent vector, one that's only going to be a length of 1, no matter what t value you plug in. All right? All right, now in part C, when we take derivatives in Calc 1, and, we understand that's a tangent slope, we're going to talk about the tangent slope at a particular spot. So let's find the value of the unit tangent vector at the point 424. Okay, now here's something we got to get used to, not just for these types of problems, but for just generally working with vector valued functions. We might be asked a question about a point in space. So understand that to answer this question, I've got to figure out what value of t corresponds to the point 4, 2, 4. And by the way, 4, 2, 4, that is on our original function, right? So the implication here is why we wouldn't be finding the unit tangent vector if we weren't at a spot on the curve. So it's 4, 2, 4 is a spot on the curve. So what value of t corresponds to that? That's what we got to answer. So now what we have to do is we have to go back to the original, right? So r of t, right? Not r prime of t, but r of t is 5t squared minus t. 2t equal, excuse me, I said equals there. 2t, 4t. So we know that that should be 4. 5t squared minus t equals 4. We know that 2t should equal 2, and we know that 4t should equal 4. Now what I suggest is we start with the easiest ones, right? So all you really want to do is just start and say, okay, well this means t equals 1, and this means t equals 1. That's easy. All right, so you solve the easiest one and then just make sure it's still true for everything else. I mean, it will be, unless I made a mistake as the one creating the problem, right? But is it true, right? 5 times 1 squared minus 1, does that equal 4? Yeah, that works, right? So that means that this point goes with t equals 1. So to answer the question, we're going to find the unit tangent vector when t is 1. So we just plug that in. 10 times 1 minus 1, 2 and 4, divided by the square root, 100 times 1 squared, minus 20 times 1, excuse me, 20 times 1, plus 21. So that's going to be 9, 2, 4, all divided by the square root of 101. Or if you want to break it up, and I don't care, it would look like this. Now I made a little, I made a picture of this on our 3D grapher. I'll admit I did not actually graph the true unit tangent vector. I graphed r prime. So I graphed actually r prime of 1 rather than the unit tangent in 1, and I just did that so it'd be a little more visible. So rather than being really short as a unit length, it's quite a bit longer. But the same idea applies here. So here it is. So here was our original curve. Here is the point we're talking about. And let's see, first of all, do we kind of believe that this is 4, 2, 4? So this point we're taking off from here. Okay, I believe that that's probably an x value of 4. I believe that's probably a y value of 2. And it looks like it's taking off from a z value of about 4. Okay, so it's taking off from the point we're talking about, and then basically from that point that vector is shooting off in this direction, and it certainly looks like that vector is tangent to the curve at that point. All right, so now we're going to do another example. Last time, understand that what I graphed there, that was just a vector, okay? But what did we do back in Calc 1? We graphed lines. We graphed tangent lines, right? So in example 2, it's asking us to find the vector equation of the tangent line to the curve r of t equals t squared in the x, t squared minus t in the y, and negative 7t in the z. And we're going to do that at the point 9, 6, negative 21. Okay. So let me go back actually to this picture here on the front page. Let's draw a picture of what it is that we're doing. Actually, you know what? Let's reproduce the picture here in a kind of rough sense. So here's my curve, and here's the point that I want to find a tangent line at. We know that, I'll do it in green, that the vector r prime of t is right here. Now, I think we could agree that a tangent line would look like this, right? So that would be the tangent line. So notice that r prime, of course, is parallel to this tangent line. Okay? And remember, when we found the equations of lines, we were always very interested in finding that vector that was parallel to our tangent line. Why? Because that was our direction vector, right? So what we're going to understand here is that r prime is the direction vector of the tangent line. So when we create this tangent line, we know what we're shooting for our direction vector. All right. And then, of course, what do you need? You just need a starting vector. Well, guess what? That's your starting vector, right? Going to that point. So if the origin's somewhere down here, then we just use that as our starting vector, and there's our line. Okay, so let's go ahead and calculate r prime first. So r prime of t is going to be 2t minus 1, negative 7. All right, but what are we doing? We need to figure it out for this point. Okay, so just like we did in the last problem, we have to say, what is t? What is t when we are at the point 9, 6, negative 21? Okay, well, we go back to our original function. We say 9 should be equal to t squared. 6 should be equal to t squared minus t. And negative 21 should equal negative 7t. Now, I think we can all agree that the third equation here is the easiest one to solve, right? So we solve it. So t equals 3, and then we just confirm, is it true that 3 squared minus 3 is 6? Yes. Is it true that 9 is equal to 3 squared? Yes. So that means t equals 3 is where we need to evaluate our derivative at. So r prime of 3 equals 2 times 3, 2 times 3 minus 1, negative 7, 6, 5, negative 7. That is our direction vector, right? It's our direction vector. So then to construct this line, okay, maybe I'll call the line, I don't know, let's call it S, okay? We're going to call this line S. So our tangent line will be S, and I don't want to use t because I've been using t this whole time. So I'm going to say it's S, which is a function of u. U is going to be another kind of common parameter value that we'll use. So we're the vector S with parameter u. And so remember what we do. We take our initial vector, 9, 6, negative 21, our initial vector. And then we say plus the direction vector, 6, 5, negative 7. Direction vector, which is kind of serving the same function as a slope, times the parameter u. And so when I put all that together, it's going to be 9 plus 6u, 6 plus 5u, and then negative 21 minus 7u. And that is going to be our tangent line. And that's something that I can plug in and check in our grapher. And so here it is right there. And of course, the only difference between what you see me typing here and what I had on paper is that, you know, this grapher just lets you use t over and over. So instead of 6u plus 9, 5u plus 6, negative 7u minus 21, I have t again. But other than that, it's the same. And look at that. Certainly looks like we've got a nice tangent line, right? That's just coming and kind of kissing this curve here in that one spot. All right, so on this next page here, we've got differentiation rules, right? Because we're talking about vectors. So, so we got to talk about what can we do with differentiation. Most of it's pretty self-explanatory, I guess. Not necessarily the notation, but just the idea of it. You know, so number one says if you're adding two vector-valued functions, you can take their derivatives separately or after you add them. It doesn't matter. I don't think that's too surprising. If you are taking the derivative with respect to t of a constant times u, that's the same as just taking the constant times the derivative. We have the product rule with, now this is where it gets a little weird. Notice how f is not bolded. So this is a function that is not a vector function. It's just a regular old function like you're used to, but it does depend on t, times a vector valued function that depends on t. So the product rule works here. So you can do f prime times the vector u plus f times the vector u prime. When we have the dot product, right? The dot product of two vector valued functions, and you take the derivative, guess what? You use the product rule here too. And sorry, I guess there's a bit of a typo. I didn't notice that. So that, I got to be real precise here. This is u of t dotted with v prime of t. So make sure that dot finds its way into your notes. And then number 5, derivative with respect to time of the cross product, or with respect to t of the cross product, same thing, product rule applies there too. And then the chain rule also applies, okay? So this is just, you know, if I say it like this, I think you'll be happy with it, but kind of looks rough when they write it out like that. It's the chain rule. So what do you do if you're taking the derivative of a vector valued function that's got a more complicated function inside of it? You just take the derivative of the vector valued function times the derivative of the inside. All right, and then down here, this is just a note that, guess what? Integration works too, or antiderivative works. So if you want to understand what does it mean to take the definite integral of a vector valued function, you're just going to go through and take the integral of each component function. So the x component, the y component, the z component, and then keep those in their x, y, and z component places. Or another way of putting this is to say, if capital R is the antiderivative of little r, then the fundamental theorem of calculus holds, right? And you can just take r of b minus r of a. Now let's actually do an example here with integration. So we've got r of t is equal to 6t squared in the x plus then 4e to the negative 2t in the y, and 8 cosine 4t in the z component. So they want us to evaluate this integral from 0 to 1 r of t dt. So that last page basically just gave us permission to do this. We're going to take the integral from 0 to 1 of 6t squared dt, and that's going to be our x component, or the I, plus the integral from 0 to 1 of 4e to the negative 2t dt, and that's my j component, plus the integral from 0 to 1 of 8 cosine of 4t dt, and there's my k component. Now the first one's pretty straightforward. This is just the power rule for antiderivatives. So, I go 6t to the third divided by 3 from 0 to 1. It's not bad. All right, but this is going to require some more work here. This one, you've done a lot of integration. You may be comfortable just doing the u substitution in your head, but I'll be a little more careful. U is equal to negative 2t, right? Because we know e to the u is a nice simple derivative. So du equals negative 2 dt, which means that du over negative 2 equals dt. So then what I get there is the integral of 4e to the u du over negative 2, and then we also, need to change our limits of integration. So put 0 in here, you still get 0, but put a 1 in there, you get negative 2. And then I think to be safe, we should also do some u substitution over here, right? So the cosine of u is nice and simple, so u can be 4t. du equals 4 dt. So du over 4 equals dt. And again, we don't forget to change our limits of integration. So this is 0 to 4 of 8 cosine of u du over 4. And that's my k component. All right, a little bit of cancellation here. Cancellation there. All right, so I think we're ready to finish this one here. This is, well, I guess I'll just do this, 2t cubed from 0 to 1. There's my I component. And then this would be, now we've got negative 2 times 0 to negative 2 of e to the u du, just to clean that up, plus 2 times the integral from 0 to 4 cosine u du for k. So of course this is just going to be 2i plus, so this would be negative 2 e to the u from 0 to negative 2 j plus, and I think the thing to emphasize here, we got a lot of work here, but notice it's staying a vector. It's still a vector in the end, right? We're preserving, what's in the x component, the y component, the z component. So then we've got the antiderivative of cosine is sine, so 2 sine of u from 0 to 4 k. So 2i, and then we've got plus, so this will be negative 2 e to the negative 2 minus negative 2 e to the 0. All right, and that's j plus 2 sine of 4 k. And we're just about there. We've got the x and y completely settled. And then here, this becomes, that's of course 1, so this is just going to be plus 2 minus 2 over e squared, right? Flip-flopping those. J plus 2 sine of 4k.